Ho aperto un po'. Giusto in inglese. So today I will introduce the last imaging modality that we will talk about. This is not really super common imaging modality, but it has, there are two reasons for me to introduce it. The first one is that I've learned in this modality for 12 years. So I happen to know it pretty well and also like it. And the second issue is that given that it is a low resolution modality, I will be able to give you some data for some exercises which are really relatively lightweight to analyze as compared to others. So it's pretty good to do some very interesting tasks. Now, nuclear medicine works on with radiations emitted from radioactive sources. Radioactive sources generally are isotopes, which means some atoms with an imbalance in the number of neutrons and protons. And when there is an imbalance, if an atom has too many neutrons, it emits an electron. If it has too many protons, it emits an anti-electron, which is antimatter. In the first case, let me switch the visualization here. Okay. In the first case, we are interested in that. Again. Okay, so in the first case, we are interested in that because when there is the emission of an electron, very often the nuclide emits a gamma photon, which is something that travels very far in matter. So if you have a beta decay in somewhere in the middle of the body, you might see the gamma ray outside of it. And in the second case, it's even more interesting because you will emit two photons, and we will see that later. The beta plus decay is the one that emits anti-electrons or positron, and this is the case often with oxygen 15, which can decay in nitrogen 15 and positron plus a neutrino. These are all things that you don't really need to know to understand how the method works, or fluorine 18. Now, we've said that in the beta plus decay, we emit an anti-electron or positron. How does that work? Antimatter is the so-called mirror image of matter, is identical to matter for all the properties we know up to the chemical level. And every particle has a corresponding antiparticle. So for an electron, we have an anti-electron or positron, which is positive because the electrical charge is flipped. The proton has the antiproton, and the neutron has the antineutron. Now, as the hydrogen exists in our universe, with antimatter, you can have the antihydrogen, which is an atom, which is made by an antipositron and an anti-electron. So the positron, like every component of antimatter, is stable, identical to its antiparticle. And it's possible to synthesize antihydrogen. And at laboratories like at CERN in Geneva, they can isolate it and keep it for 15 minutes or maybe even up to an hour. So measure chemical properties, chemical reactions. So not things at the quantum level, something at much more high scale. And they found it to have identical properties, chemical properties to normal matter. So what's the deal with matter, with antimatter, is that it cannot coexist together with matter because when they interact, they annihilate. And due to the Einstein conservation of energy and mass, if mass disappears, energy must appear out of somewhere. And so there is the process of annihilation. So if you have a positron, and that's the part that interests us for medical imaging, if it interacts with an electron, and it's full of, our universe is full of electrons, so it will happen pretty soon, they disappear together, but they emit energy in the forms of 2 gamma, which need to be emitted in opposite direction. So this is a summary. When you have a positron traveling in matter, it will keep on bouncing around with matter until it stops. When it stops, actually, it doesn't disappear immediately, but electrons and positrons starts to revolve one around the other, like it was an atom, but because the 2 masses are equal, every one of the 2 is rotating around the other. And however, they become very close, so they interact and they disappear. Indeed, the mean half-life of this process is 0.1 nanoseconds, so it's pretty quick. Now, what happens when they annihilate? Given physical laws that tell you that the sum of mass and energy is conserved and that the momentum is conserved, the photons can only be emitted of equal energy and with back-to-back energy, a back-to-back direction, which means that if you detect both of them, you have a line that tells you where the emission has been. Now, this is to summarize what happens in these cases. You have a nuclide that decays, emits a positron, which travel around in matter. This is like 1 millimeter or so, so this is the first source of uncertainty in the position, also, and therefore on the spatial resolution. And then you have the positron and the electron annihilating and emitting gamma rays back to back, which allow you to have some spatial information about where nuclides have annihilated. Now, where do we use that? In the imaging modality of positron emission tomography. Positron emission tomography is an exam that we can say it's a second-level exam. It's not like a CT which is present in every single, even most rural hospital, but is only in some of the biggest hospitals. And it works that way. You have a radioactive source inside the body, which decays, emits positrons, which then emit photons, which are back-to-back. And you have a circle of detectors all around the body. When you have 2 photons when there is when you have an emission and the positrons get emitted and both photons arrive at the detector at the same time in temporal coincidence, you have some electronic circuit that says, okay, there has been a coincidence. So you just draw a line that connects the 2 events, and you have the spatial information, and actually you get a sinogram identically to what you get in CT. How do you see these photons? You need some scintillating crystals, and you need to have some properties, because the crystals need to be very heavy to stop high energy photons. They need to be robust, transparent, because otherwise you don't see anything. And they must be small, because the crystal size dominates your spatial resolution. And they need to be able to pick up a photon every nanosecond or so. As I told you, you need to have a radioactive source, so you need to produce radioactive matter. How you do that? You do that with cyclotrons, which are devices where you can accelerate the nuclei like protons very fast, and then you hit a target with that. Once they used to be extremely complex giant devices that you had only in laboratories. Nowadays, you have these kind of devices here, which, I don't know, like in Milan, there are 10 of them in many hospitals. They are compact, so they use like 2 cubic meters, 8 cubic meters. They don't draw too much power. They are pretty heavy, especially because you have this shielding, because you have particles traveling around and bombarding things, so everything gets radioactive. So they have very big covers made of lead and water to absorb different kinds of particles. And they are, let's say, cheap. It's a very relative concept of cheap, but with €1 or so million, you can buy one, and it will last 20 years or so and produce enough radioactive substances to do, I don't know, like 200 exams a day. So it's relatively easy to acquire one and operate it. This is the scheme of how it might work. You start with something that exists in nature, like oxygen. You bombard it with protons, which you accelerate with your cyclotrons. This is a nuclear reaction happening where a proton kicks out a neutron and substitutes it. You get fluorine 18, which is, and the neutron. And fluorine 18 is unstable, and it will emit your positron in which you're interested. This is a list of the most commonly used clinical isotopes. Fluorine 18 has an half-life of 110 minutes, which is slightly less than 2 hours, which means that you constantly need to produce these isotopes. Now, with fluorine 18, you can you can produce in the morning and produce really a lot in the morning. So the cost of the production is just the cost of having the machine and having the operator. Then producing 10 or 100, it's not really an issue. You can produce and have it decay for the whole day. And indeed, there is some logistic now. You can buy it from abroad, even from abroad, and they will ship it to you. Like they produce the tracer in Innsbruck and they ship it to you by car in 4 hours. It's there. They just need to produce a lot and you have it. There are also some isotopes which live just minutes. And in this case, you need to have the cyclotron directly next to your scanning machine. Now, I've skipped a concept which actually is the most interesting one of nuclear medicine. We've talked about radioactive isotopes, but what do you do with that? Well, why would you be interested in an isotope? Actually, you are not. The isotope is interesting exclusively because it emits radiation that you can see from outside the body. If you have a radioactive source in your body and you put a detector outside, you can reconstruct where the radioactive source is. Why do we care so much about that? Because then you can chemically bind this radioactive isotope to a molecule of interest. And so by visualizing where this molecule is going in vivo, you can measure biological process in vivo, not in vitro, like generally you do with one cell in one reactor under the microscope. Here you can see it in a living human, and this is its power. I said you bind a molecule to a radioactive tracer, but what kind of molecule? And actually the answer is if you are able to do that, which is extremely complex, you can bind really anything. You can bind either atoms, which might be of interest, like if you bind oxygen, you can see where the oxygen goes in the body. But you can bind everything up to antibodies, which are huge. So it's a huge chemical structure. Or you can bind some neurotransmitters, which are very complex organic molecules. So you can see, and that's the point of nuclear medicine, you see function of the body, not anatomy. With all the other modalities, we have seen they showed you the shape of things. Instead, with nuclear medicine, which by the way has a very low spatial resolution, you see the function. So you might have two organs that look identical in shape, but you see that one is active and one is not, concerning a certain cellular process, and you say, okay, something is happening there. Now, what you've done after you get a radioactive isotope, you go to a chemical laboratory, to this kind of objects that are called modules, which perform a chemical reaction fast enough, needs something that needs to happen within 1 hour, where you tag a molecule, a drug, a radioactive drug, to the radiation isotope, and of course, all of these happen in a very shielded, sterile unit. What kind of molecules can you bind? This is the most common type of PET study. It's performed with a molecule which is called FDG, which is a shortening of fluorine deoxyglucose, which is a molecule that works identically like glucose, the sugar, the common sugar. And why are you interested in that? Because sugar is used by all cells in the body, almost all cells in the body. And so by seeing how much sugars the cells are using, you can infer something. Now, this is a PET image. It's extremely noisy and very blurry. And indeed, in most cases, it's acquired at the same time as an anatomical scan, like a CT, and then they are shown together. So you know what you're seeing here, where it's happening, in which part of the body it's happening. Now, in your body at rest, actually, most organs do not use that much sugar at all. So the so-called uptake of the sugar, of this tracer, is very low. And this is the exam of a subject. And the issue is that cancer cells, instead, usually are very metabolically active. So they pop up like bright spots in the dark. So you can identify them pretty easily. Not all of them are, like these spots here, these are the kidneys. You can recognize them better on the CT. And in the kidneys, everything that's passing in the body, in the blood, is filtrated. So, in 99% of the tracers that you can come up with, you will see uptake in the kidneys just because everything you can imagine to inject will pass by there. And indeed, you can see also very high uptake in the bladder for the same reason. But other findings instead are abnormal here. You can do many other things. I've told you can bind everything you want to a tracer. And so an example here is an element, is rubidium-82. This is a study which is super popular in the US. In Europe, for commercial reasons, we do that with other tracers that behave differently. That's a single molecule, which happens to just flow with the blood. It doesn't do much. So what do you see if you follow it from the outside after an injection? You see where it goes in the heart. And so when you have a coronary heart disease, which prevents the blood from reaching all the parts of the myocardial wall, which is the one which pumps the blood, you will see that you have a massive reduction in uptake in parts with coronary obstruction. So even just seeing where blood is flowing is of great interest. In this case, we again use FDG, which is the most common tracer, like 99% of the scans. It shows you if the cells are alive. And in this case, we've seen that we are not getting any blood on the septal wall, but the cells are alive, which means that if you go into operation, the heart, that wall of the myocardial will start to work again. And if you want to do a cardiac bypass, you need to sew open the sternum, and it's an operation that takes months to recover. So you want to know beforehand if it's going to be successful or not, because if here the cells had already died, it will be really, you will have lots of side effects to the patients for the operation, but no gains. Now, I've told you that at rest, our body doesn't use that much sugar. And this is true for all of the body except one specific organ, which is the brain. When we are at rest, lying down on a bed, our brain, which is 1 kilo, 1.5 kilos, uses 25% of our calories, of the calories that our whole body, 69 other kilos, is using. So it's very, very active. So I told you that the normal body is mostly dark, so with no tracer uptake at rest. The brain instead is super bright because it's very active. And an interesting thing, which I'll come back to in 20 minutes, is the fact that in dementia, you have, there can be many different types of dementia. But if you have a proper dementia, it will shut down a specific part of the brain, which are typical of the specific dementia that you have. And so an FDG PET scan allows us to differentiate dementia and to see that way before you can see it on an MRI, because on an MRI you will see it so late when the cells have already died and the gray matter is thinning. Here you will start to see things very early when the cells are just reducing their activity. Now, for this reason, PET and nuclear medicine has been super interesting also for research, not only for diagnosis. Like this is a paper from 1998. You will see that they were taking a look at blood flow in the brain, in the brains of bilingual and monolingual subjects, and see how it activated when a subject was exposed to his own language or a language he didn't know. And so they could see which parts of the brain were getting more blood flow and if this was different in people who knew a second language from when they were born, or late acquirers, or people that just didn't know it. But you can do much more than studying just blood flow or activation. Well, with metabolism, you can still do many things. So here, this is, like you can see from the image quality, a study again from almost 3 decades ago. Wow. Yes, the time flies. Yes. And you could see with the glucose metabolism how the benzodiazepines, these are common anxiolytics, and they were how cocaine user versus non-cocaine user reacted, their brain shut down differently after anti-anxiety drugs. No, sorry, the cable is jiggering. But as I've told you at the beginning, you can bind almost any kind of molecule and follow it from the outside. So if you are able to synthesize a molecule which works identically to something of interest like a neurotransmitter, which is super complex molecule, and you are able to tag it with radioactive isotopes, you can study multiple things. Like in this case, they were studying how they were using a tracer which is an analogous of dopamine, and they were studying it, how the amount of brain available in how much dopamine transporters were present in the brain of a smoker before and after smoking a cigarette after a period of withdrawal. And you are able to see that. There's no other modality from which you can do that. Study in vivo how the brain reacts to some drug stimulants or so on. Now you can, until now I've shown you just images, but actually with PET we can see how the tracer moves in time. And this can be extremely interesting. This is what's happening in the first minutes after an injection. This is just, in minutes, it's just moving together with the blood, whatever tracer you might inject. But this is very useful, and with some appropriate mathematical models of kinetics, you can even quantify with absolute quantification the speed of some chemical reactions in different cells. grouped with a resolution which is very low, but you can see that. Now, let's summarize this modality like we did with other imaging modalities. So with PET, you get images which have a unit of measures. The units is amount of radioactivity in a unit of volume. As an example, kilobecquerels for cc, which is not really meaningful per se, because that amount of uptake will depend on how big is your body, because the bigger it is, the more the tracer will dilute, and how much you injected, and on lots of biological properties of drug kinetics. But this can be normalized to some reference unit and give you some what's called semi-quantitative information, and in some cases even fully quantitative ones. Now, the scan time is kind of 20 minutes, even 40 in some cases. The PET scanner can see 15 centimeters, maybe 20 centimeters or 25 in the newest scanners of length of the body. So if you want to do an oncology scan, which you go from just below the eyes to the knees, that's 1 meter and something, so you need 6 bed positions, so you need 6 times 2, 6 times 3 minutes. Or if you want to go to focus on a single organ, you might want to acquire very high number of photons, so you acquire for longer, but that takes time. You need to compare that to CT scans, which took seconds. So this gives you lots of problem with patient compliance, with motion blurring, because some people might move in long time. And well, you can also do much longer studies for dynamic research studies. The spatial resolution, they will tell you it's around 4 millimeters. What you actually get is more like 5 or 6, let's say. Radiation dose is nuclide dependent. When you inject something in the body, it will remain there. So if you have a long life isotope, it will give you much more dose for the same amount of activity injected. So it's around 10 millisieverts, so it's kind of in the high dose range. So it's not really for every day, but it's extremely powerful, so it has its use. Summary, it's functional imaging, proper functional imaging. No other modality can give you that. It can be fully quantitative. In general, is extremely sensitive to most tracers because you are targeting very specific biological processes. Now, I didn't mention that, but when you inject a tracer in the body, the amount that you are injecting is truly ridiculous. You are injecting something like 10 to the 10 molecules, which is, 10 to the minus 15 of a mole. So it's something that is not chemically active. It will not modify. Your body will not even realize that the molecule is there, given it's something like one nanogram of matter that you are injecting, because given that when you count radiation, you can be so sensitive. Now, the bad size, which are a bit, is that it's the most expensive form of imaging. The standardized reimbursement in Italy for one PET scan with a so-called simple tracer is 1,500 euros, as compared to 300 euros for a CT scan or 500 for a complex MR scan with contrast media. However, you need to keep in mind that the most expensive form of imaging is still 1/10 of the cheapest form of micro-invasive intervention. So if you need, a laparoscopic examination to take a biopsy, you need an operating theater, and maybe a day hospital inpatient situation, that's going to be 10,000 euros. So the most expensive form of imaging is still better than every other alternative. It has very poor spatial resolution, half a centimeter or so. Higher radiation dose, you need contextual anatomical imaging to better to interpret the results, and it's also slow, so it's affected by motion artifacts. My last slide on that is that of what they invented for that, which is hybrid PET-CT systems, where they just stack together a CT scanner with and the PET scanner in the back using the same bed, and so you get easily and automatically two images that are intrinsically registered, superimposed. Okay, that's it for nuclear medicine. Do you have any questions on that? Because if not, I'm going to introduce First, I'm going to talk 5 minutes about dementia. No, sorry, I don't remember in which order I'm going to do stuff. I'm going to talk a bit about the way that brain images are generally analyzed. Then I will introduce, I will say some words on dementia and introduce the data set that we will use today and on Monday at least. Now, there's a concept in neuroscience which is that of standardized coordinates. The hypothesis, which is, not fully proven, but it works very well up to a point, it works extremely well, is that the same place in the brain of each human does the same task. Of course, to say that the same place in the brain of everyone does the same thing, you need to define what do you mean by same place. However, we humans are good at recognizing patterns. So if you take a brain image, you will see in everyone these specific sulci. And so you say, okay, this is, we call this around at the left of, in the front of the central sulcus, the motor cortex, and on the right, the somatosensory cortex. Then we have the auditory cortex, the primary visual cortex, and so on. And indeed, they came up with the concept of the homunculus, which is the projection on this so-called motor cortex and the sensory cortex of the human, with the shapes distorted by how much they're represented on the gray matter cortex. So you see that the hand occupies quite a lot of shape, quite a lot of the area of the brain cortex. And indeed, we have extremely fine motor sensitivity on the hand, motor control on the hand, and sensitivity to stimuli on the hand, while on our back we have extremely little sensitivity. Also on the face, we can control the movements of our eyebrows, of our teeth, our tongue pretty well, so we can speak very clearly. We can communicate using facial expressions pretty well. While, if you can perceive the temperature of the texture of a surface very well with the tip of your finger, but if you try with your back, you wouldn't feel anything because you don't have that many sensory terminals there. So what did they do to say, okay, we have the same place in every brain? The first things that they did was that of thallic brain coordinates. They were publishing atlases, actual paper atlases of the brain based on a single post-mortem study of a single brain. And the concept was that of relative differences. Because they said, okay, bigger brains have structures that are bigger in terms of volume. that are similar, but they are just farther away scaled by that. So you went with paper on this atlas, and starting from a reference origin point, you measure the reference to the structure you were investigating, and that was it. Nowadays, we have MNI coordinates, which stands for Montreal Neurological Institutes. And you could say I'm using this version here. There is the link in the PPT. And they superimposed 305 normal brains of healthy volunteers representative of different genders, age, and so on. And they registered them to another set of brains that had been previously co-registered to the Tal-IRC atlas to maintain some historical consistency. Now, when you say MNI coordinates, actually, if you go on the website that does the standardization, you will see that there are many different definitions, and they can differ by up to a millimeter in one point on the other. So you say standardized, actually standardized up to a point. When you have these standardized atlases, these standardized templates, you also have atlases, which are manually drawn by consortia, and they define regions based on anatomical markers. So you know the sulci that you can recognize, the gyri, which are the turns of the gray matter that you see on the images. Or maybe with other studies, you have functional landmarks, which are all things that you can recognize. So if you open up a standard template, you can say that it will tell you, okay, this part here is the frontal cortex, this part is the frontal left cortex, we have the superior orbital cortex near the eyes, and so on and so on. So when you report the results of a study about brains and you say, I'm seeing these in the visual cortex, there is some consortia that helped you in identifying where the cortex is, that visual cortex or whatever it is. Now, this is a pretty old school approach. It hasn't been superseded, and has been going around since, I would say, probably Tal-IRC was from the 70s already. And now, starting from the 90s, what they started to do with software, some standardized analysis using, especially using the general linear model. So as a data scientist, you should know that ANOVA and t-test. So what they did was to collect many images. They could be, let's say, you take 20 PET scans, 10 of healthy subjects and 10 people with Alzheimer's disease. You warp all the brains to the reference atlas, and you can take a look at all the images in this standardized space. Now, the next things you can do, that it is done, is to apply a heavy spatial smoothing to the image. This has two reasons. First, to remove all the image noise, actually most, and then also to not take a look at very local anatomical differences. Even if you had infinite spatial resolution, you wouldn't want to use it. But you say, okay, I'm going to take a look just with on what's happening on a scale larger than X millimeter. By heavy, we mean 8 millimeters, or sometimes even 10 or 12, even nowadays. Then when you have these many images in this common frame, smoothed out even to remove biological variance, not only technical variance, you just do a pixel-wise, pixel by pixel, general linear model. It can be, I don't know if you have my simple example, Alzheimer's disease subjects and healthy controls. You do a voxel-wise t-test. you can also do a regression, like you have patients with some deficit that you can measure with a psychological scale, and you do a regression, and you plot the R squared as a function of, and you do a linear regression and plot the R squared of every pixel of the brain. So you get what's called a statistical parametric map. This can be a map of Z scores, of T scores, of F scores from ANOVA. Then there is a last issue, which is to estimate statistical significance. So we are doing voxel-wise regression. How many voxels you have in a brain, even if you're working at 4 millimeters resolution, give or take 100,000. And of course, the issue of multiple comparisons with 100,000 parameters estimated is a really huge issue. But the even worse issue, which actually on one side it saves you, but on the other one is terrible to deal with, is that these voxels, given that you apply the super heavy smoothing, are by far not independent. You are working with 1 millimeter voxels or 2 millimeter voxels, and your spatial resolution is 1 centimeter. So there would be a correlation even 10 voxels away in all the 3 directions. So what they did was to develop a pretty strong so-called random field theory to take into account the correlation function of all the voxels. And they could get some statistical significance map. And of which you, by the way, you can define in multiple ways, because if you have a single bright spot of extreme intensity, it's probably significant, statistically significant. But if you have, I don't know, 10,000 voxels, each of which nearby, contiguous, each next to each other, where each one does not reach statistical significance, but it's 10,000 and contiguous, this is not a, this cannot be a random finding. So you need to combine all of this information, and it's not trivial nor unique the way to do that. So those who want to enter neuroscience research, which is on one side a fascinating field, on the other side full of type 1 errors, let's say, this is very fascinating. We will not go deep into that, but we will start analysis also with more advanced techniques. The interesting part of that, for which is still used today, instead of artificial intelligence, is that giving you a map of locations after a t-test feels, more than is, feels interpretable to the neuroscientist. Because if you say, you can measure like any parameter this way, even how much the gray matter is thick locally. If you say, on these kind of subjects, the gray matter cortex is thicker in a statistically significant way in people with this pathology as compared to the other, they think it's an interpretable finding. So that's why you still use it. Now, all of this introduction to introduce the dataset that we will use today, which is a dataset about dementia and the use of FDG PET. I've mentioned briefly before that different types of dementia are associated with specific damages to specific parts of the brain. Indeed, cell metabolism is one of the first aspects to be impacted. Now, this is the so-called theory because it's not proven, and we don't know what's happening with Alzheimer's disease. Actually, they invested like 20 billions of US dollars in anti-Alzheimer drugs that targeted the so-called amyloid cascade, which I'll tell you in a second. And it turned out that they if you fix the amyloid issue, you don't fix Alzheimer's, so we still have no full idea of how the Alzheimer is working. Now, if you do a post-mortem analysis of a healthy brain and a brain with severe Alzheimer's disease, this is what you get. Everything is shrinked, especially the gray matter cortex, which is the outer one. Now, if you do an ideal plot of a biomarker abnormality, I introduced biomarker, it's something that must be quantitative and measurable, and you put, let's say, a detection threshold, over time, you have that decades generally, but also that varies massively from patient to patient. Generally, a decade or so ago, before symptoms appear, the amyloid present in the cerebrospinal fluid starts to increase. Then, if you do a PET scan, which is able to take a look at the amyloid load, this starts to increase. By the way, these two biomarkers, however, are pretty sensitive, but they are not specific. That might also increase in people which will never develop Alzheimer's disease. Then also another protein starts appearing in the cerebrospinal fluid. Finally, you have alteration in the FDG PET images. The metabolism of the brain starts to change. And finally, when you do neuropsychological assessments, you start to see some specific reduction of the capability to solve some tasks. And these are the kind of subjects which are called MCI, which means mild cognitive impairment. And with Alzheimer's disease, one telling symptom is short-term memory that starts to reduce. As you can imagine, this is extremely not specific. So this is something that always happens with Alzheimer's, but it happens for many other reasons. And only when it's full-blown, you can say, okay, this is definitely Alzheimer's, but also there the gold standard is not 100% sure. You are sure only with pathology, with post-mortem pathology, but of course that won't be available. But there are many different types of dementia. A very common one is the called, it's not a specific kind, it's arteriosclerosis, or also called vascular dementia. If you start to have, due to circulation, issues with oxygenation of your brain, with circulation in your brain, blood circulation in your brain, you start to get your brain capacity reduced with some symptoms which will change according to which part of your brain has been affected. So it would be completely aspecific because vascular disease can appear anywhere in the brain. You have two other types of dementia, DLB, two other popular kind of dementia. Dementia with Lewy body, which is this kind of biological origin, and it has, again, the problem with everything brain-related, lots of unspecific symptoms, both neurological and psychiatric. So you have mood swings, hallucination, starts being unorganized, and things like that. Each one individually is not specific at all. There's also the frontotemporal dementia with behavioral variant. Again, this is also extremely unspecific symptoms. Well, these can be kind of specific if they appear all of a sudden in someone that never had them, because you have lack of social inhibition, lack of interest in doing anything, difficulty in keeping jobs, start of repetitive behaviors, and also there is unusual accumulation of tau proteins in the brain. If you do a group analysis of FDG images in the way that I've shown you before, a t-test between healthy and non-healthy subjects, and these are like 20 subjects against 100 subjects, you get an extremely specific pattern. So what you can see here is that the frontotemporal dementia starts with the frontotemporal lobe of the brain, of course, shutting down. With Lewy body dementia, you can see the brain shutting down again in the parietal cortex, but not in the occipital cortex. Sorry. And also the occipital cortex, while in Alzheimer's disease, you have this area in common, but not this one. Now, to do the analysis that I've introduced you in PET, starting from images that are coming to the scanner, you need to perform a spatial normalization to this MNI space, then the spatial muting, and then you get an image in kilobecquerels for unit of volume. You need to bring all the images, which we said is not meaningful. You need to bring all these images to the same kind of intensity value. And how do you do that? It's pretty up to you, let's say. You can scale the intensity to some reference region. You can use either the whole brain, so which means scaling to the mean of all the image. This makes a lot of sense. Or you can use regions which have been proven not to be affected by some specific pathologies. Now, a database for which we will work, and you could work for your projects, is the Alzheimer's database, Alzheimer's Disease Neuroimaging Initiative, which is started, I think, in 2005. It's a study which is described by these words, which you should probably have seen in the other module of this course. It's a multi-site. You acquire data from lots of sites. Longitudinal, it means that each person is followed at multiple time points. Prospective, so you don't collect data afterwards when a patient asks the patient to bring you the data of previous exams. You first enroll the patients, then you follow it. Naturalistic, so you don't do any intervention. Study of normal aging, mild cognitive impairment, and early Alzheimer's disease. This study collects really a lot of data. MR images, like for some subjects every 6 months you get a couple of MR images that show you the brain structure and not only. Cerebrospinal fluid markers, PET images nowadays also with not only the cerebral metabolism, but also amyloid and tau, and peripheral blood biomarkers, and also neurological and psychological tests. There are thousands of subjects collected, divided in multiple phases, with the phase 1 starting in 2004 with 200 normal subjects, 200 clearly evident Alzheimer's disease, and 400 subjects with mild cognitive impairment, which being as such a non-specific definition could easily develop into Alzheimer's, but sometimes not. There was a challenge a couple of years ago, the Tadpole challenge, which was, and it acquired, they were providing you a curated data set, because of course the Alzheimer's data set is massive, and the first thing you need to do when you want to do a study, this is freely accessible, by the way. You need just to do a request for access on the database, justify your project, and you're given access to the database and download whatever you want. And you, in this specific challenge, they created some pre-processed and created some data, and they asked the participants to predict conversion accuracy. Okay, so that's it, my part on how you do some neuroscience analysis and on dementia. Do you have any questions? Okay, so I've uploaded on the drive. Let me share my screen. Oh, but by the way, I wanted to ask you a question. How well do you know autoencoders? Have you studied autoencoders in other courses? I see one yes. It's in the room. Okay. So for the next lecture, I will prepare some summary of of how you might build one, let's say, and what it is and why you would want to build one. No, sorry. So I have put this folder where I have uploaded some data. We have 4 folders of data, which is healthy controls, Lewy body dementia, behavioral variant frontotemporal dementia, and Alzheimer's disease. In each of these folders, we have some data saved in nifty format, which you can read with nibable. And the letters S and W at the beginning is a neuroscience convention, which means that this data have been warped to the MNI space and smoothed with an 8mm kernel. So these images are images on which you can already do what's called, you know, like the T2, the t-test that I've shown you before. Here in the masks folder, I have some masks that you can use to select just some part of the brain. And I've put a Jupyter notebook that asks you to set up a kind of classification using standard methods, let's say, traditional ones. But of course, you can invent something you want. Images, even if they are, people think of images like something to be displayed, it's still vectors of parameters that you can, for example, just put directly as they come in a PCA algorithm, maybe. So if you want to, I've suggested a way to look and modify this data, but you can invent one yourself. And in the next lecture, we will introduce a method to do automated analysis, like, again, with autoencoders and some unsupervised classification. And then first I will introduce autoencoders, then I will tell you how you can use it on this same database. Okay, so any questions about that? Okay, so you can start and ask me whatever question you encounter.